Welcome to section 4.9. We're going to be looking at something called the antiderivatives. And with an antiderivative, it's really just doing the opposite of what we do when we take the derivative. We're just going to be moving in the opposite direction. And then all of chapter 5, we're going to be doing that technique, going the opposite way of taking the derivative. And so section 4.9 is serving as that link between chapter 4 and chapter 5. Okay, so let's define what an antiderivative is first. A function f, capital F, is called an antiderivative of a function little f on an interval I if the derivative of capital F is little f, all right, for all x and I. Okay, so let's look at a quick example. Let's say big F is equal to something like x cubed. Then little f would be the derivative of that function. Okay, so little f in this case would be something like 3x squared. And now normally what we're going to do in this section and in chapter 5, we're going to start here with a little function and we're going to be going backwards to figure out the antiderivative. Okay, so we could say this. So 1, because we'll talk about how there can be more than one antiderivative, but one antiderivative of f of x equals 3x squared is big F of x equals x cubed. Okay, so let's try an example where we start here. So we're given a function and we want to find the antiderivative. Okay, so let's now find the antiderivative of f of x equals x to the 4th. And we're going to find the antiderivative, okay? So this means if we want to find the antiderivative, what it's really saying is we want to find a big function, find f of x, where the derivative of that function is x to the 4th. All right, well, let's think. So this is a power function. So we know, like here, let's go back up to this example. We know when we take the derivative, we bring the exponent down and then we subtract 1, right? And we would get 3x squared. So if we're going the opposite way, so going from f to the antiderivative, well, the opposite, instead of subtracting, here we'll go like this. So we're starting here, make a little chart, and we want to go to f of x. All right, well, we know when we take the derivative, we'll go this way. All right, and up here we said it was x cubed. When we take the derivative, we subtract 1 from the exponent and bring that 3 downstairs, okay? So we subtract the exponent. And since going the other way, This is the antiderivative direction. We're going to do the opposite. Instead of subtracting 1 from the exponent, we're going to add 1 to the exponent. Okay, so that takes care of that, and then we have to find out that coefficient. So that's kind of our strategy, right? So right now we're here, we have x to the 4th. We want to find the antiderivative. So doing the opposite, we're going to add. All right, so we're going to take our, what is it? Our f of x equals x to the 4th. And we're going to find the antiderivative, okay? So again, we're going in this direction. And so we know we have to add 1 to the exponent. Okay, so we're going to start, so this is our f, this is our f. So we're going to start with x to the 5th. And then we have to think, all right, so we have the exponent correct. And now going in this direction, you know, when we take the derivative, what do? Well, we bring the exponent down, and then we subtract 1. All right, so there's subtracting 1. And if we were to take the derivative of x to the 5th right now, it would be 5x to the 4th. Okay, but our coefficient for f is 1. So really, our original function to make that coefficient 1, if we want to end up with x to the 4th, we have x to the 5th, but the coefficient would have to be 1 over 5. Because now when we bring that 5 down, right, 5 times 1/5 is 1, right? So we would have the 1/5, and then the derivative of x to the 5th is 5x to the 4th, and they would cancel, and that would give you your x to the 4th. So the antiderivative is 1/5 x to the 5th. All right? So let's see if we can think of the pattern. What if our f function was now x to the 27th? And we wanted to find the antiderivative going in the opposite direction. All right, well, what do we do with the exponent? We are going to add 1. Okay, so I'll write out all the steps. Oh, 27 plus 1 is 28. Okay, so we're going this way, antiderivative. But when we go in the opposite direction and we take the derivative, we would bring the 28 down in front, but the coefficient is 1. So we're going to have a 1 over 28 in front, and then that would be your antiderivative. Okay, so in general, if f of x is a power function, an exponent function like x to the n, the antiderivative moves backwards again. Okay, so we're going to add 1 to the exponent. And actually, hold on. I'm going to say a single antiderivative, and we'll talk more about that later. So, sorry, one antiderivative is we add 1 to the exponent, and then the coefficient has to be 1 over n plus 1. And now when we take the derivative of this, right, we bring down the exponent, the coefficient becomes 1, and we're left with x to the n. Okay? All right. So that was the pattern we saw. So let's try some examples, or let's try one example. Let's say we're looking at 6 x cubed, and we want to find the antiderivative, f of x. All right, well, let's just focus on x cubed because this is a constant, so we can worry about the constants at the end. Well, what's the antiderivative of x cubed? We add 1 to the exponent, and then the coefficient is 1/4. All right, and again, now when we take this derivative, we bring down the 4, coefficient becomes 1, x cubed. Bam. All right, and then what's 6 times a fourth? How's that going to simplify? 3/2, right? Okay, so the antiderivative of 6, or one antiderivative of 6x cubed is 3/2 x to the fourth. All right, and again, that f, all right, that function that antiderivative we just found is just one of, believe it or not, infinitely many antiderivatives. Okay, for instance, I'll just say f2 of x, I'll make some silly notation, of 3/2 x to the fourth plus 5 is also an antiderivative, because go ahead and take the derivative of that. What do you get? You get that 6x cubed. And that's because what's the derivative of constants? It's 0. So I can add any constant to this antiderivative up here, and I'm going to get a new antiderivative. And there's infinitely many constants, right? So we have something called a general antiderivative that captures every single antiderivative. So the general antiderivative, we state it like this. We say f of x is the antiderivative, and then we say plus c, where c is an arbitrary constant. Okay. All right, so let's look at some general antiderivatives of all of the functions we've had so far. And it's not going to be an exhaustive list, but let's just practice. So we have a column for f of x, and then we'll also look at the antiderivative, capital F. Antiderivative. Okay, so we've already done one, the power rule, x to the n. The antiderivative, the function whose derivative is x to the n, is this. And then how do we make it the general antiderivative? We add c. We'll add plus c. All right, and let me make a little note. This is true for all cases except if n is -1, right? So let me write that in. N, in this case, is not -1. All right, if n was -1, x to the -1, that's like 1 over x. Okay, and what function has a derivative 1 over x? The natural logarithm. Okay, something like that. And remember, logarithms have to be positive. So we'll just think of this as, absolute value, natural log of absolute value of x plus c. Okay, so let's keep going. Let's say our function was e to the x. What's the antiderivative? What function has the derivative e to the x? That's our favorite one, right? It's just e to the x. The derivative of e to the x is e to the x. Let's look at another exponential function, this time with base b. And so we have to think, what function has derivative b to the x? All right, well, we know b to the x, that derivative is b to the x times the natural log of b, okay? But we are not multiplying by the natural log of b, so it must have been canceled out. So normally when we take this derivative, b to the x, it's going to be b to the x natural log of b, right? But we don't have this. So again, it must have been canceled out. So there's probably a natural log of b in the original function. All right, and remember we have all of our trig functions. So let's think like this. Let's say we have cosecant x, cotangent x, and we have to think what function has the derivative cosecant cotangent. Well, we know the derivative of the cosecant is negative cosecant cotangent, but this one's positive. So that means the original function must have been negative. Now when we take the derivative, it will be the opposite of the negative cosecant cotangent. Minus minus becomes plus. All right, so you see how we have to kind of change our way of thinking a little bit? All right, and then, you know, we have more functions. We still have all the hyperbolic stuff, but we can look at something like this. And we can think, what function has this derivative? Going through our Rolodex, we'll remember that the inverse secant has that derivative. Okay? All right, so let's practice with more complicated functions. Let's find the antiderivative of the following function. R theta is equal to secant theta tangent theta minus 2e to the theta. Oh, wait. Let me show you this. I'm sorry, I just realized something up here. Let's go through and just to make it, how can we make it the general antiderivative? We can add c's. All right, there we go. Now it's a general antiderivative. Before it was just one, now it's the general. So it says antiderivative. We'll find the general antiderivative, because why not? So we have to think we're going backwards. So remember, r prime of theta, capital R, is going to be equal what we're given. So we're going to go the opposite direction. We have to think, what function has the derivative secant theta tangent theta? Well, the derivative of secant theta is secant tangent. So there you go. All right, and then here also, what's the antiderivative of e theta? What function has the derivative e theta? E to the theta. That's our exponential function. It's just e to the theta. And then finally, what can we do to make this the general antiderivative? We can add a constant. All right, and the cool thing about all this stuff is we can always check our work. And we check our work to make sure that our theta is equal to little r. All right, so for instance, the derivative of secant theta is secant theta tangent theta. And then the derivative of negative 2e to the theta is that. And then the derivative of a constant is 0. All right, and then that's exactly what little r theta is. Okay, so we're able to easily check our work for the antiderivative. We can just take the derivative and see what we get. All right, let's do that again. Let's look at some more examples. So let's look at this. All right, and then we want to find the antiderivative. And rather than thinking how we can go backwards with the quotient rule, right, let's not even deal with that. Let's use a trick that we used when we were evaluating limits and when we were finding derivatives for the first time. we can separate this fraction up. Excuse me, yeah, we can separate the numerator up, right? We can take each term in the numerator and divide it by the denominator. So like 3t to the fourth divided by t to the fourth minus t cubed divided by t to the fourth plus 6t squared divided by t to the fourth, okay? And then we can come up in here and use some exponent rules, or just, cancel out. So we have 3 minus, this is going to be 1 over t, and then plus 6 over t squared. I'm going to write it like this, though, t to the negative 2. All right, I put the t down below because we're finding the antiderivative, and that's a special case. Okay, so now we are ready to find the antiderivative. So we have to think, what function has the derivative 3? That will be 3t. The derivative of 3t is 3. All right, and then here's 1 over t. What derivative has function 1 over t? Well, that's the natural logarithm. And then you can throw in those absolute value signs if you'd like. All right, and then finally we have our last one. We have to think what derivative, or what function has the derivative of 6t to the negative 2? All right, well, we can start off slow. We can ignore the 6 till later. We're going to add 1 to the exponent, so negative 2 plus 1 is negative 1. And then you figured we have to divide out by that exponent. All right, so we're multiplying it by negative 1. Something like that. All right, so then let's clean it up. So we have 3t minus natural log of the absolute value of t, and then 6 times negative 1 will be a minus 6 t to the negative 1. And then to make it a general antiderivative, we add a constant. All right, so let's try some examples on your own. So I'm going to give you 3 functions, and you're gonna find the general antiderivative. All right, so after you guys have the functions, go ahead and push pause, and we'll see how you guys do. All right, so g of x equals 2 cosine x minus 3 divided by the square root of 1 minus x squared. So find the antiderivative. F of x equals e squared. And then the third one, h of x equals the cubed root of x squared plus x square root of x. All right, so let's see how you guys do on that. So push pause and then come on back. Okay, so here we go. So number 1, the antiderivative. Okay, so this big G, when we take the derivative, we're going to go back to little g. Okay, so d dx will get us back to little g. So we have to think, what function has derivative cosine? Well, the derivative of sine is cosine. So that's that. That's not so bad. And then we can ignore the 3. So I'm going to kind of move that constant out to the front. And now to think, what function has derivative 1 divided by the square root of 1 minus x squared? Oh, sorry, with a negative sign in front. So we can think of this next part 2 ways. We can think of it like this, right? Because subtraction is like adding a negative. And if we think of it like that, Well, the derivative of negative 1 over the square root of 1 minus x squared is the inverse cosine. Okay, ooh, let me stick that 3 in front as well. So we can do it like that, right, plus the opposite. If we want to think of this as minus subtracting a positive 1 over square root of 1 minus x squared, well, then the function that has that derivative is the inverse sine. So either one of these is going to be correct. It's just how you guys view it. And then how do we make it general? We add c. Okay, so these two are both correct answers. All right, and again, they're both correct because it just depends on how you're viewing it. All right, and then number 2, e squared. Well, e squared is a constant, right? You can plug it in your calculator, you're going to get one answer. So the function whose derivative is a constant, right, we're just going to add an x because the derivative of x is 1. Okay, and then to make it general, we're going to add c. Okay, so again, number 2, we have to remember that e squared is a constant. And the antiderivative of a constant is just that constant times x. Okay, and then for part 3, before I would hop to it, I would rewrite it. I would rewrite cubed root of x squared as x to the 2/3. Right, because remember this index is an exponent of 1 over 3. So 2 times 1/3 is 2/3. And now this, I would add the exponents, 1 plus 1/2, because we're multiplying. All right, 1 plus 1/2 is 3/2. Okay, so now we can take the antiderivative a little bit more clearly. So it's going to be the same process even though they're fractions. All right, so just like so even though they're fractions, it's still the same process. So for instance, whose derivative is x to the 2/3? Well, we're going to add 1 to 2/3. So you can do a little math. 2/3 plus 1 is like 2/3 plus 3 over 3 is 5/3. All right, so that's this exponent of the antiderivative. And now the coefficient is going to be 1 over that exponent, so it's the reciprocal, 3/5. All right, and then we can do the same thing with x to the 3/2. 3/2 plus 1. 1 can be written as 2 over 2. It's 5/2. And so the coefficient is going to be 1 over the exponent, which is the reciprocal. All right, and then how do we make it general? We add c. And remember, we can always check by taking the derivative and making sure that the derivative of h, big H, gets us back to little h. All right, so in part 2, we're going to figure out ways that we can find c for different situations.